Yesterday, Paul Whitewick from Whitewick's Abandoned Railways posted something on Twitter about the box tunnel. So, Whitewick's Abandoned Railway YouTube channel you should definitely watch. So, somewhere is the link. This tunnel is somewhere next to Bath, I assume, and it's one of the tunnels of the Great Western Railway, constructed by Brunel himself. And this tunnel has a 1 in 100 incline, which is quite steep, and people were worried about runaway trains reaching something like 120 miles an hour and killing a lot of people. So Paul also posted that he would like to be able to calculate this stuff, and I thought, hey, I'm a physicist, this is mechanics 101, I should be able to do so. So get a gin tonic, paper, and off we go. So let's start. We have an incline, which has the train going downhill and a couple of forces. So first there's the resulting force which the train is accelerated with, which is just force mass times acceleration. And then there are various forces which sum up to this resulting force. So there is the gravitational force. There are various resistances. So there is the air resistance, Fa. There is the rolling resistance, Fr. There is some kind of inertia, which is caused by rotating wheels and stuff like that. So that's called that FB. Okay, gravitational force is quite easy. We have gravitation pulling downwards. There's the incline, which has an angle alpha. So the resulting gravitational pull is pretty straightforward. It's mass times gravity constant times sine alpha. The air drag, Fa, is a bit more complicated, so I looked it up. It's 1.5 times the drag coefficient times the area of the engine times the density of the air times the velocity of the locomotive squared. Rolling resistance, Fr, is given by m times g times cosine alpha times a coefficient, Wr. This coefficient is something you would probably look up or guess or something. And there is the rolling resistance, Fb, which is also a constant, Ei, times mass times acceleration. So we already see there's the velocity and there's the acceleration in some of these forces. So let's write acceleration as the first derivative of velocity, so v dot. Then we put that all together. M times A or M times V dot is minus mg sine alpha, because it's going in this direction, plus mg cosinus alpha times Wr. I'm resorting that a bit to make it a bit easier, so I first get all the mass dependent and then I get the velocity dependent thing. Plus Ei times m times v dot plus 1.5 Cw a rho v squared. So I can now resort all that and put it in a different form, which gives me 1.5 CW a rho v squared minus M1 minus EI v dot plus M times G times WR cosine alpha minus sine alpha equals 0. So to make stuff easier, I call this part capital C, this part capital D, this part capital E, and end up with C v squared minus D v dot minus plus E equals 0. C, D, and E are constants given by the weight of the train and the area of the train and various other constants. And you see already there's a v squared, there's a derivative of v, so this is a differential equation. And the problem with differential equation is they're hard to solve. So I could put in the constant values here and then put it in to Mathematica or Octave or something, some computer algebra system, and I would end up with something which looks a bit like this. So when you put this in as a general solution without any boundary conditions, you get a tangens hyperbolicus from T, which is something which looks like this, which is what you expect. So at some point in time, the speed reaches a maximum speed limit. This is the complicated way of doing things. But fortunately, there is a simpler way. We are interested in the final velocity. And the final velocity is reached when there's no acceleration left. So all parts which are using acceleration are cancelled out. So the resulting force is 0. This is 0 because there's no acceleration anymore, so you don't have any what do you call it, acceleration resistance, and we're just left with these terms. So in a steady state, we have an infinite incline and the train is just rolling downwards, and just you're in a balance between the gravitational force and the air resistance and the rolling resistance, which means we have the gravitational pull mg sinus alpha, and this is equal to the air drag CW a rho v squared plus mg cosine alpha. That's the rolling resistance. And this is a simple equation where we just have a v, which we can easily solve. So we get v equals square root of 2 divided by CW a rho times m times g times sine alpha minus WR. There's a WR here missing. Cosine alpha. And this is the final speed. So if we now take a classical engine, so this is the Adler, this is a German locomotive, but Paul suggested a Great Western Railway locomotive, Castle class, I think, which I couldn't find the weight, to be honest. So I choose a slightly earlier one, a Firefly class. Firefly class has a mass of 24. Firefly class GWR broad gauge, has a mass of 24 tons. Then we have, what else do we need? We need the air density, which is 1.2 kilogram per cubic meter. We need the front area of the locomotive, which I did a rough guess. So this thing is, broad gauge is 2.2 meters, I think. So probably it's 2.5 meters wide and something like 4 meters high. So let's just take 10 square meters to make it easy to calculate. Drag coefficient is something I also need to guess. Drag coefficient for a modern train is something like 1.2, so it's probably a bit worse, but not too much, so just let's put 1.3. What else do we need? Alpha is 1 in 100 is 0.57 degree. And then I can put all this in there. I still need WR actually. WR. This is something I looked up. That's the rolling resistance coefficient, which is for modern train engines something like 0.0025, 2 zeros and then 25, and then just let it put 0.3 for bigger wheels and more resistance and whatnot, and put all that in, calculate, which I did with the help of a pocket calculator, and we end up with a Vmax of 14.5 meters per second, which is roughly 50 kilometers an hour. So if you just let the train roll and get into a steady state where it's just fighting air resistance and there's no additional push from anything, you end up with 50 kilometers an hour, which is something like 40 miles an hour, 35, something like that. And which is far less than the 120 miles an hour that people feared. So this is quite an interesting result. You see, it's really dependent on the mass. So if it depends on the square root of the mass. So if I double the mass, this goes up by 1.4. If I quadruple the mass, this doubles. So if I have 4 times the mass, so instead of 24 tons, I have something like 96 tons, which is probably what a train would be, then I'll end up with 100 kilometers an hour. You see, the maximum speed of the Runaway train isn't getting nearly to infinity, but it's just 100 kilometers an hour, which is actually less than I would expect it. But there's probably still some mistake in my calculations. What you didn't see in the video is about 8 hours of hectic calculations, and you don't know how many mistakes you can make with mixing up minus and plus and missing out terms, and yeah. So I haven't done any serious calculus in years, so this was quite fun to actually calculate something again. So I hope you enjoyed that a bit, and cheers, and please follow Paul Whitewig and Whitewig's Abandoned Railways, and hope to see you soon. Cheers.